Hi everyone, thank you for coming. HubAI is very pleased to be hosting today's event looking at artificial intelligence in medicine. So for that we are hosting Sonja. I forgot to check how to say Sonja's last name. Aits.
Aits.
Sonja Aits. Very, very, very nice. And you're an A. I was always jealous of people with A's. I'm a T, so I'm always at the bottom of the list. But anyway, so now, Sonja, you are part of everything, it feels, and anything, because AI is so broad and medicine is so broad. So when I look you up, you have a ton of keywords to your name. You have neuroscience, cell and molecular biology, bioinformatics, and systems biology, biochemistry, molecular biology, and all these things. And I'm a bit sad to say I don't really know what many of these things mean. So I really can't wait to hear more about what you do. And yes, so from Rafsan and what he was telling us, you have been, so Rafsan was on the panel discussion 2 weeks ago. He was explaining how artificial intelligence has been hugely beneficial to get a lot of information very quickly, especially in times of COVID. So can't wait to hear about that aspect, and also all the projects that you're involved in, because you're involved in AI Lund, in compute, in I'm afraid you'll have to give even more of a presentation of yourself, because
No.
so much. So yes, I can't wait to hear more about you. And lucky I could have gone by what you've written, your little description, although even that makes it sound like you're not as involved as what you truly are. So thank you so much for accepting to come and talk to us today, and I can't wait to hear more about this. Thank
Well,
you.
it's my pleasure. Thank you for this lovely introduction. So yes, I'm Sonja, and I am just a regular person, not a robot, even though it just made it sound a little bit different. But yes, so I'm a cell biologist by training to start with. So I study biomedicine. I have a PhD in biomedicine. But then I got too much data to handle, and this is why I branched out into artificial intelligence. So I will give you a kind of couple of examples of what we do. Please feel free to ask me anything afterwards, really like broadly, even if it's like just vaguely related to what I talked about. So that's no problem. So you maybe all know this feeling sometimes that you have too much information to actually make sense of it. In medicine, we really have this problem. We have a lot of information, a lot of different types of information. We have thousands of patient journals that potentially have valuable information. We have millions of scientific articles written and also other text. We have so many bioinformatic databases that we actually have databases of the databases. And we also, of course, have very nice and very large data sets from single experiments, which can be like millions of experimental data points, for example. So you can have like, I have, for example, from an image-based screen, I can 6 million images from one experiment. And, you know, other people have similar type of data from genomic experiments. You have massive amounts of data and so on. And all of this is lovely because potentially this information we have can give us clues as to how diseases work, how patients respond to individual treatments or to diseases, can help us find new therapies, and it can also kind of help us design the best public health strategies. So it's great that we have all this information, but the problem is it's completely unstructured, most of it. And that means that we can't actually get there. So we can't use this information because it just exceeds human capacity. And that means we have a problem. And this is what led me to the AI. So there are different types of AI. Of course, we often, when we say AI, what we mostly mean by in practical contexts is machine learning. And there's different types of machine learning, as you all of course know. And I will talk about two versions of that today. One is natural language processing and the other is computer vision. So when I refer to NLP, I mean natural language processing. And what is that? Basically, it means a computer can read text or understand like spoken words, or even generate text or words. So when I say we have a lot of data, so what do I mean? For example, we have a database called PubMed, which collects more or less every medical article that is written with at least an English abstract, and there are about 30 million in that database, stretching back to, you know, the 1900s. So this is a lot of information, and you may think, okay, this is all of the medical data, but if you're a medical researcher, it's not like you're doing all of medicine. So do you really have this issue when you're just looking at a specific field, for example? And I can give you one example, which is kind of current. So this is articles about coronaviruses. This is a disease that was discovered less than a year ago. Of course, there were other coronaviruses before, but they didn't have the same impact on a global level. So interest has been kind of over you know, since the 2000 has been somewhat, but then it has exploded. So as you can see, we have more than 300,000 research articles written about coronaviruses already. So even if you're a specialist only trying to understand coronaviruses, this is beyond what you could process. It's impossible to read in the time you have, but it's also impossible to keep in your head what you have read and to try and find the connections between these pieces of information that you find in different articles. So it's basically like when we have the information, it's like finding a needle in a haystack. Say we're looking for a new COVID drug, for example, but it's not. It's even worse than that, because we actually have the needles, so to say, scattered over many different haystacks. And what do I mean by that? So, for example, imagine this scenario. We could have an article one, maybe written 15 years ago, from the field of, say, oncology, and it discovered that a drug A has a strong connection to the gene B. Great. 10 years later, someone in a different field, say diabetes research, finds a very close connection between the gene B and gene C. Also great. And then maybe someone last year, or rather in the last months, I mean, discovered that gene C is a critical target for COVID-19. Great. The likelihood that the COVID-19 researcher will have read article 1 and 2 is basically zero, because they're from completely different fields. So it's, even if they search, they would probably miss this type of information. So if you instead use computers to process all the text, what you can try to do is put this information together into a pathway. And then you could see that maybe drug A is something that should be tested for a cell model for COVID-19 or an animal model. So I'm not saying that the text analysis will give you all the answers, so don't get me wrong. But what it can do is that it can help you find potential candidates for drugs, for example, which you then have to verify biologically, of course. So I wouldn't suggest that you do some text mining and then start treating some patients. So there's, of course, steps in between. But you can narrow it down in this way. And here's an example for COVID-19, but of course the same principle you could do for any kind of other disease, or even for just figuring out biological processes and not even related to disease. And of course you can exchange drugs against genes or proteins or mRNA or any other type of biological entity that you're interested in. So how does it actually work? So in most of these cases, you have as a first step something that's called named entity recognition. So a named entity is basically a phrase or a single word that corresponds to a typical class that you might be interested in. So this could be genes, or this could be drugs, this could be diseases. And so this is just an illustration, kind of, which I've hand labeled, but you would see what you could kind of labeling you could do with a computer-based system. So you could label all the different type of classes. And then that doesn't help you all that much yet, because you still, I mean, you have your text and you know what is what, but it doesn't link it together. So for that, you first need to connect these named entities to a specific ID. And the reason for that is that so many of the proteins, for example, they're referred to by very different names. So people use different synonyms for the same thing. And if you want to connect it, you need to kind of link everything back to one entity. And often we use kind of an ID, for example, from one of the established big databases. This could be either the gene symbol, for example, or it could be a UniProt database ID, or any other. It's basically, you can choose what you want to use, but you should use something that's widely kind of used. And then the next step is the even more important one. So once you have your entities and you know which ones they are, then you can also try to find relations between them. So for example, in this sentence, you can find two entities, SARS-CoV-2 and ACE2, which is a protein. And then you can find that the sentence describes that they have a relation, namely that one binds to the other. So on this type of relations, whether it's binding or whether it's activation or inhibition, for example, is what you can identify with a text mining tool. So often in the past, people have written very long lists of names and their synonyms, for example, and then kind of just done exact phrase matching for the named entity recognition. And then for the relationship, they have maybe written very complicated rules saying, you know, if the word in between is a verb and it has some part of it that says activate, then it's that, and if it's inactivate, then it's that. So it's, but you can see how with the amount of synonyms we have and the different ways we can express ourselves, how this will fail eventually. So these systems are not performing very well. So what we do today instead is that we actually use machine learning models for doing this instead. And the type of models we use, they're extremely large and complex. So they can have billions of parameters even to train. So because you often don't have that much training material to start with, what we do is that first you train a language model. This is the type of model that we are using for NLP. So you first train it on a very large corpus, and a corpus is nothing but a collection of text. So this could be, for example, an English language model that is trained on the entire Wikipedia and 1,000 books. And from that, this model gains a basic understanding of the structure of English language, for example. And that doesn't get you to the end result. For that, you need to actually fine tune on the specific target task and corpus. So for example, you can use a general English language model and then train it for named entity recognition or train it for relation extraction. And you do that on a specific set of type of text, for example, on medical journals or on PubMed articles. And the trained language models in the middle, you don't need to train them from scratch every time, because all they have is the general understanding of the language. So basically you can share them and reuse them, and this is what's being done. So many of these have a type of architecture underlying that's called BERT. And then we have, you know, adaptions for the biomedical domain, which are called BioBERT, SciBERT, or BlueBERT, and these are basically shared, so you use them as a starting point. Nevertheless, even though we have these nice models now, and they are much better than the dictionary-based methods alone and the rule-based methods, it is a challenging problem. Natural language processing is hard because language is hard, even for humans. If you think yourself, how often do you misunderstand a friend? How often do you ask a clarifying question when someone explains something to you? A model cannot do that. It has to work with what it got, so to say. And you can see this, we have this nice sentences, you know, it's only the domain knowledge or like the general world knowledge that will help you understand. If she said she killed the man with the tie, so did she use the tie to kill the man, or was the man wearing the tie? And the same, I mean, that is maybe harder, but for example, the second sentence, the inspectors send restaurant staff home because they suspected disease transmission. In the context of this pandemic, all of you know exactly what this means. But they didn't, it wasn't the restaurant staff who suspected this is disease transmission, of course, right? It was the inspectors. But this is something that just from the grammatical structure of the sentence is ambiguous. So this is why it's hard for the models to actually get this 100% right. And the ambiguity is not the only problem in NLP. So we have also things that we call co-reference. For example, we use terms like this disease, this terrible pandemic, or something like this. And we all know what we refer to, but it's not using the correct word. And if it's an article about Parkinson's disease, this disease could refer to something completely different. We also use lots of synonyms or even synonyms expressions. You know, you can explain the same with a verb or with a noun. And we have lots of abbreviations, of course, negations and uncertainty. And of course, also some of the content in articles is basically not true because there's also bad research. So this is not always easy. But nevertheless, it's very useful, and we can, of course, also use it for other types of text. So this is another project we have, which is related to getting information not from scientific literature, but from electronic health records instead. So these are basically the patient journals we have. So there's a collaboration with the doctor from the hospital in Malmö. And what we're trying to do is extract information from the journals of acute medicine patients. And this could be something like tagging the symptoms, for example, or tagging other diseases. And from that information, then afterwards, calculate which symptom combinations are the most common in COVID patients or in COVID patients that have a bad prognosis and so on. The reason we can't just simply use have the doctors fill in, you know, all the symptoms in a structured way is just because there is no time for them to do even more admin while they're doing emergency care. So they just write in these 3 sentences, and there's of course a lot of variation depending on which doctor has written it. But in general, you could say whatever text you give, it can give many different applications. So just in the context of COVID, you could analyze health records or scientific literature. But if you're a social scientist, maybe you want to analyze social media posts or news reports. And all of this you can, of course, do in a way with the same tools. So it kind of depends on what you want. The same as you know, the tool reading can let you do very different things depending on whether you read, you know, a comic or a theoretical physics book. So it all depends on your point of view, and you, even for the AI models, you just select the task and the target, so to say. So another type of data we have a lot of in medicine is images. So we don't just have a lot of text, we also have lots of images, and that's also a type of unstructured information. So for example, one type of images we have, these are photographs of cells in a microscope, and the bright little white spots that you see there, these are broken lysosomes. So stuff like that I would count during my PhD manually with a little clicker. So, you know, and if you experiment and you maybe have 20 different conditions to test, and you have, you know, so and so many samples, you can imagine how many hours I spend with a clicker. Do you want to count dots like this? I don't think so. Well, I didn't either, and now I don't have to anymore. So now you can have a computer that counts them for you. So that basically the punchline is that computer vision allows PhD students to do more fun and useful things, so than counting dots. So this, of course, is nice for the PhD students, but it also means that we can scale up massively. So before, you know, a single student could maybe handle, you know, counting 10 samples in an afternoon. But if we use a computer-based systems, of course, we can process millions of images in the same time. So this enables much larger scale microscopy. So for example, we can do experiments in this type of plates, which have 384 samples in one single plate. And with this, we can then load a robot, have lots of different conditions, even plated the cells and the treatments in them with the robot. And you can have hundreds of these plates in one experiment. So for example, I did a genome-wide screen where you remove every single gene in one well, and that gives you several hundred of these plates, each with 384 little samples, and for each of those samples you take 48 images. With a microscope that looks like this, it's just a box. Actually, it's a normal microscope underneath. The only thing is that it's robotic. And then you get images like this, lots and lots and lots of images, often in several different color stains. And like I said, from one experiment, you can get like 6 million, for example. And then you process them on the HPC cluster, because that's obviously not something you do on your laptop anymore. And the first step is often just finding the objects on the images, which we call segmentation. I will talk a little bit more about that in a minute. And then once we have found the objects, then we can do all kinds of measurements for each. We can, for example, see the length, the size, the shape, the texture, the intensity of the stain, and so on. And from that, we can see that if we have 2 samples that have a similar type of cell in the images, then we know that these two are these 2 samples have related effects on the cell. And from that, we can, for example, connect biological pathways, and just by basically guilt by association. So samples that are similar often come from related pathways. And then together with other information that maybe says that some genes bind to each other, we can put together such networks. So the first step in this case would be to find the objects. We often, even though microscopists like to show these pretty pictures, which are colorful and beautiful, we actually usually work with something like this. So the color ones, the same like this that you see right now in the screen behind me, this is of course more beautiful and for human eyes, but for the computer you just used grayscale images. So you separate the different color channels into grayscale. And then you can annotate, for example, the outline. So here we do have a little bit of manual labor again, but it's basically something you do once, and then you can, train up your model with this. So you just, sit. Basically, you could sit with a pen and a pad, or just with your mouse, click the outline of the objects, and you maybe annotate 50 such images. And from that, you can train a model. In this case, it's a UNet, which has a convolutional neural network in one arm, and then kind of the inverse on the other arm. And that it gives you this type of predictions. And this is real annotated outlines and a real prediction that was done by a master student in my group. And you can see how similar kind of you can get. We also do computer vision, of course, not just for finding objects and outlining them, but also for classifying images. And here you, for example, see tissue sections. This is lung tissue. We have a collaboration with a lung engineering group. So we look at classifying damaged tissue versus normal tissue. So the little purple objects you see in this are cells, and the white space is just background. That's because your lungs are mostly filled with air, and this is what they should look like. But this is something that you can train a computer to classify, and then you can process much more samples and much more reliably. And of course, you can also classify other things. So we have, for example, also projects where we classify images by quality. So trying to classify blurry versus non-blurry objects, images, for example, or even do multi-class classification. And I know that there are other projects in Lund University elsewhere where also people do a lot of image classification, for example, for radiology, because currently, for example, we have thousands of women that undergo mammography screening for radiology every month. And we need to process these images. And I think currently a trained radiologist has about 40 seconds per image to make a judgment call. And this is still the bottleneck. So if we can train up computer systems, it can go much faster. And there's groups in Lund here that work on this type of work as well. So this all sounds lovely, and it is, and it has huge promise, but it doesn't mean that it is without challenges. So first of all, the AI models are not yet smarter than a 3-year-old. So if, for example, what I mean by this, if you can have models that are fantastic at recognizing, chairs, planes, types of cells, or whatever. If you disturb the image somewhat, for example, in this case, turn the chair upside down, you can fool the model tremendously. So this type of things is, really problematic. It could be the same that you train a model that works well on one type of microscopy image, but if you switch the microscope, it suddenly doesn't work anymore. So this is something that we don't have a general AI in any way. We are very highly specialized models that work often only on a specific type of data set. Also, then, they can be fooled by noise. For example, if this like variable detector noise or something like this, this is an actual image from a publication a couple of years back, where you see that the model gives kind of somewhat confidence that the left image is a panda, but you add some noise and it's almost 100% certain that this is a gibbon, which it obviously isn't. And, a 2-year-old would be able to tell you that this is a panda, but, an AI model cannot. So, of course, people are trying to make these models more robust and so on, but don't be fooled that even minor things, and these may be things that you don't know about, can really throw off your model. And maybe if you're, just doing something that is not life and death, then maybe it's not critical. But if these models are to be deployed in the clinic eventually, this can be decisions that cause serious harm, actually lead to death of people if the decisions are wrong, right? So this is very problematic that we have these problems with the model still. And of course, we also know that we have very biased data often, because, for example, a certain type of disease may only be, all the clinical trials maybe were done with white Caucasians, and then maybe the models work terribly when they get images from another group of people. Or, you know, many medical data sets from clinical trials come from men, because you may want to exclude women due to the risk of pregnancy. And then, you know, you may have a gender bias in your data set. And as with kind of any type of research, if you put garbage in, you get garbage out. But often the problem is that you're not aware that you're putting the garbage in. And this is really something that's important. And this is where this whole discussion about, you know, transparency of AI models comes in, that you really try to find ways of making things not just a black box, so that you can troubleshoot this much better. There's, of course, also privacy concerns when it comes to medical data. So this is basically the most sensitive type of data we have almost. And it might not be as private as previously thought, because AI models today are in many ways so powerful that they can connect the dots, but this means they could also connect the dots from different data sets and use that information to de-anonymize people. And that is especially true for patients with rare diseases, for example, where we may only have 10 or 15 cases in the entire country. So this is something that is of utmost importance, that we kind of are aware of these issues, and when we deal with this type of data, that we handle it appropriately. And this is even more important considering the fact that there's now companies in the healthcare and AI business that do have some, say, doubtful privacy policies. So this is something to keep in mind when you're on, you know, social media, or when you're using any of the other tech companies, businesses, as I do as well. It's just the fact that you know that these companies are also aiming to become healthcare companies in a big scale. So it's, you know, just be aware of what you're sharing, and, you know, make mindful decisions. Some people may be totally okay with sharing, and that's also good, but just, you know, be aware of it. And nevertheless, I think that overall AI can find and link information in medical big data, which otherwise we couldn't find or couldn't use because it's too complex for us as humans. So I think there is a great potential of using these technologies for all different types of medical research. But I also see that we will also see this type of technologies broadly applied, not just in the research field, but actually in healthcare. So, you know, we will have systems that help us collect patient history, for example, everything from voice recognition to the kind of smart apps that you may have on your phone, fitness connected to a fitness band, maybe monitoring your blood pressure and so on. We will also have automated diagnosis tools. This will hopefully shorten the time that it takes to get a diagnosis, but also it will make diagnosis accessible to countries where today they don't have access to trained pathologists or trained radiologists in the same extent that we have here in Sweden, fortunately. And eventually we will move also towards AI systems that at least give treatment recommendations. They may not do the final decisions, but they will, you know, assist doctors and maybe highlighting related studies for a rare patient and so on. And then, you know, through the whole kind of chain, we'll have surgical robots, we'll have logistic systems and also so on. So I don't think there will be many areas that won't be touched by AI in some way, in the same way that, you know, the internet and computers have become very prevalent. You can do it many different things with it, and people will do, I'm sure. So if you think this is a super interesting field, which I hope you do, I just wanted to make you aware of a few training opportunities. So we have the Compute PhD School, which has a course package related to AI in medicine and life sciences. We've had one course and we'll have more next year. The ones this year were postponed due to the pandemic to enable the medics to attend. We've also put together quite a lot of information on our own group's GitHub page, where you find, you know, anything from online courses to book recommendations and so on for different types of data science and machine learning. And then I just want to thank you all for listening, but also all the wonderful people I work with. This is obviously not just my work. Much of the hub programming is actually done by my wonderful students and many wonderful collaborators. And of course, we also get lots of money for paying the wonderful students and doing this type of research that we do. So thank you.
No, thank you. That was really amazing and quite mind-blowing. So much. I got really envious of your trained data thing because I'm trying to do a systematic literature review right now. And so all this data. And I was like, how do you train your data to tell you what it's telling you?
But actually, this is a good point which you just mentioned. Like, so I mean, one of the key applications of this text mining technology, it could be systematic reviews, because it could do the, or at least, you know, being part of the kind of triaging, so helping the researcher find all the information, even if potentially the author hasn't used the right keywords in the abstract. And then, you know, maybe highlighting key phrases for you, and maybe extracting some kind of information about sample sizes and so on automatically. So I think this is, we've had also some discussion with the Cochrane people here. They are the ones that make systematic reviews for medicine. So I think there's a lot of potential in this area.
Great. Well, I'll have to look into it, ready for next week, I guess. But so from that perspective, actually, did you want to stop sharing your screen so that we could
I can do that, sure.
see each other? And maybe if, for whoever wants to, if you want to put your webcam on. Yeah, so my question is, like, how do you train the actual labeling? Because is that all done by a human to like, how much is there human input to train the data?
In those systems we're using, this is mostly human labeled. So the annotations that I showed you, the real ones, these are made by students who actually sit with a mouse and, you know, click the outline of the cell. So you have quite a lot of manual label, so to say, to some extent, but then you also do heavy data augmentation. So in order to train such a unit, the one as I showed you, we used maybe 30 labeled images for training, to combined with some data sets that have also been labeled by others, but also combined with like rotation and flipping and other types of augmentation. So it's not as bad, so to say, as it sounds. Like you often say, like, you need kind of tens of thousands of examples to train the machine learning. This is no longer true, especially if you make use from transfer learning as well. So for example, also for the image classification, we can see that if we make use of models that are pre-trained on other types of image classification, then we don't need as many labeled data, so to say. Sometimes you're also lucky and you actually have a training set where no one needs to actively label. So for example, for this lung project which we have, I mean, we basically got a data set from the lung group that says these are samples where we know is tissue damage because we have introduced the tissue damage. This is experimental data. This is not from patients. So we know that these are healthy tissue samples, and these are damaged tissue samples. And then you know the label basically without someone having to sit there and actually kind of go through and score them. And I mean, you can do the same way if you would, for example, have radiology images. You could just see which of the women actually did get breast cancer afterwards, and then you use that as a positive label for your radiology images. So sometimes you can get around it and don't use human labels, but there is still quite a lot of human effort, especially also for the text annotations. Yeah, I mean, sometimes you can use automated kind of suggestions, and then you have a human kind of correct the errors, which can be faster. But I don't think you can really get around the human part completely yet.